This is our third and final video on solutions. In our last video, we had just discussed the different ways to solve a molarity problem, either in steps or using dimensional analysis, and we had also discussed how to solve a backwards problem. Let's do the two examples. What is the molarity of H2SO4 if 49 grams of H2SO4 is present in a 250 milliliter solution? So, stepwise, you would do 1. I'll take my 49 grams divided by the molar mass of H2SO4, which I get from my periodic table, which is 98. When I divide those, I get 0.5. I then would take my 250 milliliters divided by 1,000 and get my liters. And then step 3, I divide both numbers, and I get 2.0. Molarity. Okay. In addition, or instead, you could have also solved this using dimensional analysis. Oops. So let's erase our answer here, and then we'll do it the other way. So you take your given grams, your 49 grams, divided by your given milliliters of 250. 1 mole divided by your molar mass here. And then 1,000 milliliters over 1 liter. You'll get the same answer. Want 2 for 2 sig figs because of the given values. The second problem is a backwards problem. You would know it's a backwards problem because it's asking for grams. You have to first convert your milliliters to liters. So we'll do that by dividing by 1,000 and moving our decimal 3 places. And then I follow the 2 steps. So step 1, I take my liters times my given molarity of 0.5. And you end up getting 0.0625 moles. And then step 2 is that I take my moles, multiply by the molar mass of my substance, which ends up being 180 grams per mole for this substance. And you end up getting about 11 grams when you round for sig figs. Okay. In reality, you should be able to solve for any of the 3 pieces. You could be asked for grams, you could be asked for moles, you could be asked for molarity, you could be asked for liters or milliliters. Okay. At this time, you should pause the video and try the 3 practice problems. Please check your answers to the practice problems. The first one, even if you solved it the steps way, should have still given you 0.31 molar. For the second one, it's a backwards problem because it's asking for grams. So I converted my milliliters to liters, multiplied liters times molarity, which would give me moles, and then multiplied by molar mass. Feel free to do all of that in one step. For question number 3, we use the triangle. We're going to cover up the liters because I want milliliters. I'm going to take moles divided by molarity. So I convert to moles here. And then I divide by molarity to get liters. And then there are 1,000 milliliters in a liter, so I multiplied by 1,000 to get my milliliters. Okay. All of these would be fair game on the upcoming test. Let's continue our study of calculations. Dilutions are another type of calculation. When we add water, we decrease concentration, so we're diluting it. Okay, that should hopefully make sense. The moles before and the moles after should still be equal. The equation looks like this. It's M1 V1 equals M2 V2. So it's very similar to like Boyle's law. for the gas laws. You're going to be provided with 3 numbers, and you solve for the 4th. Okay. The word of in the problem indicates that those numbers stay on the same side of the equation. So in the example, it says 2.0 liters of a 0.88 molar solution get diluted to 3.8 liters. What is the new molarity? So this is V1, this is M1, and this is V2. And you simply just plug your numbers into the equation. So M1 times V1 equals M2 times V2. And you solve algebraically to get 0.46 molar. Okay. At this time, please pause the video and try the 2 practice problems. Here you can see the answers to the practice problems. Both really just kind of plug and chug, so plug in what you know and solve. For the second question, it's a little different. It asks you to describe how to make your solution. So you have to use your M1V1 equation to figure out how much of the stock solution you need. Turns out you'll need 117 milliliters, that's your V2. And then for this question, you'd also have to make note that you have to dilute the solution with water up to 250 milliliters. So you do the math and then also briefly describe how the solution is made. Continuing on, there is stoichiometry in this unit. So solution stoichiometry, just like all the other stoichiometry we've talked about, has a generalized equation that usually works. So it is here, liters of the given over 1 times molarity of the given, we'll talk about what all this means shortly, over 1, followed by your balanced equation step where you put the coefficient of what you want over the coefficient of the given, and then it's 1 over either the molarity or liters of what you want. Okay, these problems are going to provide you with 3 numbers. The given is the one that you have both the molarity and the liters or milliliters for. Okay, so let's run through this practice problem here. It says how many liters of 0.250 molar barium chloride are needed to form 0.0325 liters of a 0.160 molar NaCl, and it should say solution there, sorry about that. You have to remember that the main goal of stoichiometry is to take what you're given, turn it into moles, then use your balanced equation to convert to a new type of mole, and then convert back out. So you go from your given to moles so you can compare them with your mole bridge, and then convert back out, which is exactly what we're doing. So we're going to go ahead and do the math now. So we're going to take our 0.0325 liters of NaCl over 1. We're going to multiply that by 0.160 molar NaCl. Liters times molarity gives you moles. Balanced equation, I want BaCl2. I have 1 BaCl2. And I'm going to be creating NaCl. I have 2 of them. Okay, or excuse me, I'm not creating NaCl. I'm removing the NaCl. And then it's going to be 1 over the given molarity of barium, which is 0.250 molar. Okay. So I'm converting to moles, converting back to moles of something else. Then moles divided by molarity gives me liters based on my triangle. And you should end up getting 0.0104 liters for your answer. Okay. At this time, you should pause the video and try the second practice problem there. Since it's asking for milliliters and it gives you milliliters, you can keep it in milliliter form. Okay. So pause the video now and try it. Please check your work. So the KCl was the given because you have both volume and molarity for that. Then I have my balanced equation step. I want PbNO3, so that goes on top. And then I have 1 over the other number in the problem. And you should get right around 18.8 milliliters. You would know it's a solution stoichiometry problem because you'll see an equation of some sort, and you would see that there were 3 numbers given with the equation. So this is what makes it different from a typical dilution. In addition, you're comparing 2 substances, so the KCl and the PbNO3. The final part of the chapter, or this section, is on colligative properties. A colligative property is defined as a property that changes when a non-volatile solute is added to a pure solvent. Non-volatile is something that does not evaporate easily or at all sometimes. So like salt or sugar. It is dependent on two things. The concentration of solute as well as the number of ions in the solute. Okay, we don't do the math for this, but this is called osmolarity, usually, or it's related to osmolarity. Okay, there are 4 properties that we are going to discuss in detail on the next 2 slides. You may want to pause the video if you don't have a copy of the PowerPoint and copy down this table and the table on the next slide. Let's discuss the first colligative property, vapor pressure lowering. Vapor pressure is defined as the pressure above a liquid. The vapor pressure goes down when a solute is added. Normally, when it's just a pure solvent, such as water, the number of molecules that turn into a gas equal the number of molecules condensing back into a liquid. When something is added like salt or sugar, the added solute takes up surface space and basically creates a barrier. That barrier does not allow molecules to become a gas as quickly as the gas molecules are returning to be a liquid. So what ends up happening is there's less crowding. Okay, so there's less molecules above the liquid, and therefore vapor pressure goes down. Osmotic pressure is the pressure required to stop osmosis. Okay. There are 3 major types of solutions here. We have an isotonic solution where there's no net osmosis. It's shown here. It's equal concentrations on both sides of the cell. We have a hypotonic and a hypertonic. Hypotonic, the concentration inside the cell is greater than the concentration outside, so water will go into the cell and it could burst. And hypertonic is the opposite, so water leaves the cell and causes it to shrivel. This is actually what happens to slugs when you pour salt on them. The last 2 colligative properties are boiling point elevation and freezing point depression. Okay. Boiling point elevation. Boiling point in general is the temperature when the vapor pressure of the liquid is equal to the outside atmospheric pressure. We just learned that adding solute decreases vapor pressure, so more energy, an increase in temperature, is needed to re-increase it so that it equals the atmospheric pressure. Okay, they're all connected. Salt and water is a good example of this, as well as antifreeze. Freezing point depression is the opposite. Freezing point is the temperature when the vapor pressure of the solid equals the vapor pressure of the liquid. So since the vapor pressure of the liquid decreases when I add a solute, the vapor pressure of the solid must as well. This is done by lowering the temperature and the energy to cause something to freeze. Salt on the roads in the wintertime is a good example of this. This concludes our study of solutions.